participate in one session, and you
Yeah.
gave me an opportunity. So really thankful.
Definitely, sir. Raj, are you there? Dinesh?
Sunil sir, சொல்லுங்க.
இருக்கீங்களா? Okay, okay. Right. இல்ல, இருக்கீங்க.
No, I
I
told
think
the audience actually will be starting exactly at 2:40.
2:40, okay, right.
Oh.
Sir, people are joining. We'll wait for another 4-5
yes,
minutes.
yes.
Up to 2:40 will start.
Yes. But I'm happy to see that a lot of people have joined almost on time.
Yeah.
About 20-25 people have joined dot on the time. So it is a good sign that we are now being more punctual, respect the time appointments.
Yeah.
Good to
Yes.
see.
Yeah, thank you. Yes, sir.
செந்தில் சார் ஸ்டார்ட் பண்ணிக்கலாமா?
பண்ணிடலாங்க.
Okay. Good afternoon, everyone. Very warm welcome to all of you for joining us today. I hope actually everyone is doing well actually. On behalf of Indian Institute of Foundrymen, Chennai chapter, it gives me a great pleasure to welcome you all for today's technical webinar on the topic, how melt quality and shrinkage defects are linked. We have an eminent speaker with us, Mr. Sharad, Dhumane, a highly respected Foundry consultant along with us for running through this webinar. Before we move forward, I request our chapter chairman, Mr. Sendil Kumar, actually to do the welcome address.
Very good afternoon, fellow Foundrymen. It gives me immense pleasure to welcome you all for this technical webinar organized by Institute of Indian Foundrymen Chennai chapter on the topic of how melt quality and shrinkage defense are linked. At the outset, I would like to extend a very warm welcome and respectful welcome to our esteemed speaker, Mr. Sharad, Dhumane, sir, a highly experienced Foundry consultant, a well-known personality in the Foundry fraternity. Sir, we are truly honored by your presence today. We know each other for a long time. I think thanks for taking time out of your busy schedule, giving for this wonderful webinar session. This topic, we had a couple of topics from sir, and then we had an interaction locally, and then we chosen this interesting topic. Melt quality and shrinkage defects are two critical aspects that directly impact casting quality, rejection rates, and overall productivity. Understanding the linkage between these two factors is essential for improving process control, reducing defects, enhancing overall foundry performance. I am confident that today's session will help all participants gain practical insights that can be applied in day-to-day operations. I also warmly welcome all our members, industry professionals, and participants who have joined this online platform. Your enthusiasm to learn and upgrade your knowledge is what keeps our fraternity strong and progressive. I once again welcome you all for this session. I request all the participants to make this best use of this opportunity by actively listening, engaging, and raising questions during the interaction sessions. Thank you all. Wishing you a very informative and engaging webinar. Thank you. Over to you, Raj.
Thank you, Sendil sir. Thank you, Sendil sir. Actually, before we move ahead, actually, already everyone, Sendil sir and myself said actually he's a well-known person actually in the market, but still, I like to introduce him actually to the gathering. It's my privilege actually to introduce our esteemed guest speaker of the day, Mr. Sharad Dhumane. Mr. Dhumane is a highly respected Foundry professional with over 4 decades of rich hands-on experience across operations, metallurgy, quality assurance, and new product development. A metallurgy graduate from IIT Kanpur, he has built a distinguished career working with leading organizations such as Kirloskar Ferrous Industries, Ashoka and Works, and Wasp Castings, where he has held key leadership roles, including chief metallurgist and plant head. His core expertise lies in metallurgy, process control, rejection reduction, yield improvement, and implementation of new technologies. A certified Six Sigma black belt, he has consistently driven operational excellence and quality improvements across multiple foundries. Since 2017, Mr. Dhumane has been Thank you. Sorry. Since 2017, Mr. Dhumane has been actively contributing as an independent consultant, supporting foundries in defect elimination, cost optimization, and advanced metallurgical solutions. He is also a passionate knowledge contributor, conducting technical workshops, writing for leading industrial publications, and mentoring professionals across foundry ecosystem. His global exposure and strong technical network keep him closely aligned with latest advancements. We request all the audience to keep your mic on mute, please. His global exposure and strong technical network keep him closely aligned with the latest advancement in foundry technology. Notably, he has also contributed to initiatives aimed at developing foundry education and skills actually at an international level. With such vast experience and practical insights, we are confident that today's session will be extremely enriching to all of us. Without any further delay, I invite Mr. Sharad Dhumane to take over the session, please. Thank you.
Thank you, sir. I really overwhelmed by your kind words. And basically, I loved the opportunity offered by Mr. Senthil Kumar to conduct a webinar. And then currently, this particular subject of melt quality and shrinkage defects is there in my mind for quite some time. And I have been writing on it on LinkedIn and discussing it with various clients, various platforms. So I really am thankful for giving me this opportunity so that I can speak about my thoughts on this particular subject, and hope that it increases our awareness of this very crucial aspect. Thank you. So before we start the discussion, I would like to uh, go back to the day when we were supplying to Aisher, and one of our batch of diffuser hubs in ductile iron had failed miserably. There was a huge rejection. My voice is clear. Uh,
Yes, Sharad ji, we can
Yes, sir.
hear
Yes,
you
sir.
loud and clear.
okay,
Go
okay,
ahead.
okay, okay.
Yes, sir.
Yes, okay, okay, good. So we were really worried, and Aisher had informed that their assembly line would be shut down next day unless we supply them parts in the morning. And we got this information when my managing director called me at night at 9 o'clock and then said we have to give them 50 parts and we don't have any parts. So So we rushed to the plant. Then we called the pattern maker. We assembled all the team members, and then we decided some action. The pattern shop immediately worked on it, and then made some changes. We literally burned the midnight oil. So that was a very challenging time. So and then around 3 o'clock we poured the castings. At 5 o'clock we knocked down the castings, sent them to the fettling area, and then I went home. And then around 9 o'clock, my final inspection head he informed me that castings are ready for dispatch and the vehicle is now leaving for Aisha. So we fulfilled that particular critical time of at least not uh, shutting down their assembly line. Then luckily the parts came out well, but still there was some rejection. So we continued another batch, and then it also did not really improve the matters. Then their executive director also visited our foundry, and then we all sat down, and then we decided some more trial, and then we conducted those trials. And meanwhile, somewhere at some point, the defect vanished. So, and then whatever we sent, those all came good. And then, so we luckily we came out of the problem, but it remained in my mind that what really had gone wrong. And I did not really understand at that point of time. We looked at all the data, and then whether it was holding time, or it was molding sand, or it was some inoculation, or we looked at all angles, and I could not really understand why that particular event had occurred. Later on, then as I moved into other foundries and encountered similar problems in another parts, and then slowly started realizing that my methoding was not a problem. See, when I do develop a methoding for some part, and then I make some trials, initial samples, I get some 10 samples. Those are free from shrinkage and other defects. Then I take a bigger batch of 50 parts, and then those 50 parts also come out well. And then we release that methoding to production for bulk production, and then they make hundreds of parts, and then there is no rejection, no shrinkage defect. And then one fine day, we see shrinkage defect, and then we immediately, the knee-jerk reaction is that to make changes to the methoding, not realizing that the same methoding had given us hundreds of parts which did not have shrinkage defect. So there was something else which had caused that shrinkage. And since all those days, I used to think that shrinkage only depends on methoding. So we really worked on methoding, and then I realized that methoding and shrinkage defects are firmly linked when we have obedient materials. Obedient materials means they are really disciplined. They follow certain laws, and then so we can study those laws, and then we can predict their behavior, and then we take action, and those actions stay. They are sustainable actions. They ensure that our parts do not have those shrinkage defects. So materials like steel, stainless steel, then aluminum alloys, copper alloys. So these are obedient materials. So they follow those laws very obediently, and we rarely have a problem in this grade. But gray iron and more, especially ductile iron, they follow different patterns. And so when we are working with these materials, we have these problems, these issues, and then we have to understand what really is the problem. So unless we understand the process, the mechanism, we don't. So many of the foundries then go through the same experience which I had when we had to supply parts to Aisha. So the lesson which I then realized is that whenever shrinkage problem comes, methoding is the last thing which we should touch. So we should then analyze what really went wrong, and then so gradually then now I'm sharing my screen of today's presentation. So that is how then I was thinking about presenting these thoughts in a structured manner, and Mr. Senthil Kumar gave me an opportunity. So here we are. How melt quality and shrinkage defects are linked.
Sharadji, we can't see your screen.
Oh, sorry. Let me go back. Share screen. Is it okay now?
Yes, here you go. You can go to full screen.
Yes.
Perfect.
Good. Yeah. All right. Thank you. Okay. So that is how then I came up with this idea of making a presentation, and I have been writing on this subject also. A couple of my clients, whenever I go, I also talk about this. So this is a very important subject as far as our controls on shrinkage defects are concerned. Okay. So what happens when a substance is heated? So why we are talking about this? So I'm just now approaching the subject of shrinkage and melt quality from the basics so that we understand it deeply. So here you see there are two items in blue balls, and the distance between them is D. So when we raise the temperature, the D increases. So the distance between two atoms increases as we raise the temperature. Suppose we take a bar like this of a length L, and when we raise the temperature, the length L also increases. So basically, whenever heat is applied to a material, the material expands, the volume expands, the volume increases. So this is what happens whenever a substance is heated. There are few exceptions, but I think most generally this is the norm, and this is applicable to our work, our subject today. So what is shrinkage? So now we understand that when we heat something, some material, it expands. When it becomes liquid, then it expands even more. The atomic distance is much more in liquid than it is in solid. So naturally, the volume of liquid is much more than volume of same solid. So here if we consider that liquid has weight W, volume is V1, and its density is delta 1. In solid, the weight remains same. Volume is V2 and the density is P2. So the liquid density will be lower or liquid density will be higher. Liquid density will be lower because the volume has increased. So density of solid is more than that of liquid. This is very important. So what happens when the liquid of this volume, V1 volume, it's solid, it becomes solid, the weight remains same, but the volume now from V1, it has become V2. The density has changed from P1 to density P2. And V2 is less than V1. This is important. The volume of solid is less than volume of liquid. So this is the point where our problems start. The mechanism of shrinkage, because the volume of liquid is more, and when it becomes solid, it shrinks, and that difference between the two volumes V2 and V1 is called shrinkage. It is called solidification shrinkage. So it happens for almost all or most of the alloys, most of the metals, that when they shrink, there is a reduction in volume, and that reduction in volume is called solidification shrinkage. So whenever a liquid becomes solid, there is a shrinkage involved. There are very few exceptions. Coming back to ductile iron solidifies differently. So it is not like steel, stainless steel, aluminum, or copper alloys that they simply go on becoming solid, and then the solid volume is less than liquid volume. That doesn't happen in gray iron or ductile iron. So how it solidifies differently? So here there is a phase diagram. So you can see this is the liquid point. Here our material, we have heated it to this point, and then from this point it starts cooling down. This is a phase diagram. So on this diagram, this is your percentage carbon, and on this scale there is temperature scale. So for this particular chemistry, whatever chemistry here it is, so for this particular carbon content, we are here at this point, and the metal is now solidifying, and then at point A, it starts becoming solid. So the first nuclei of solid start forming at point A. And then from point A to point B, it goes on solidifying. The liquid volume decreases, the solid volume increases, and then at point B, the whole material then converts into another solid content of different phases. So solidification happens at this particular line. It starts at this particular point A and it ends at point B. At point B, then everything becomes solid. So this particular zone I have highlighted or encircled by a red dotted line. So this is called mushy zone. Why it is called mushy zone? Because it is slowly, the whole liquid is slowly changing into solid. It doesn't become solid at a snap. That now it was liquid and then now it has become solid. So it happens only when we are at the point E. So here the whole liquid becomes solid suddenly. But at all other points, the liquid takes time, and from it goes through a particular temperature range, and then it solidifies. So this is called mushy zone. In mushy zone, the material is semi-solid, like Fevicol or our Fevicol. So in Fevicol, we combine two compounds and then make a mix them together, and then it becomes ball, and that ball it has some plasticity. It can expand, it can take different shapes. So it is in a mushy condition. So similarly, the material, when it is solidifying from point A to point B, it is in a mushy condition, and this zone is called a mushy zone. So the whole solidification occurs in a mushy zone, and this particular then temperature range from A to B is called a freezing range. So these are important points to understand what really happens when the material is solidifying. Okay. Okay. So up to here it is okay. Everyone, we are not yet into complex ideas. We have just talked about how material solidifies from point A to point B, and then since it is not exactly solid, not exactly liquid, it is semi-solid or semi-liquid, so it is called mushy zone. And then after point B, it becomes fully solid, and then this temperature range A to B is called freezing range. So only we have discussed only this part in this particular slide. Okay. This is all actually experimental data. So experiments have found that solidification shrinkage reduces. Solidification shrinkage, that means the reduction in volume between liquid to solid. So that is called solidification shrinkage volume. It reduces as carbon equivalent increases. So as carbon equivalent increases from this point towards this, the shrinkage decreases. So that is an experimental data. It is called, so it has become sort of guideline for us to decide what carbon equivalent we should operate at to have a reduced solidification shrinkage. So it helps us to decide our composition grade to match the property requirement and also the requirements of feeding. So we want a grade, a composition where the shrinkage requirements are quite low and still we are able to meet the properties. So this is an experimental data which says that as we move from carbon equivalent towards 4.3, the solidification shrinkage decreases. But after this particular point, it increases again. So you can see this freezing range is increasing. Here, freezing range, as we move from this point to this point, it is decreasing, but here onwards, it increases again. So we can consider that as freezing range decreases, the solidification shrinkage decreases. As freezing range increases, the solidification shrinkage increases. Okay? Simple. Simple. Okay. Okay. Yes. Okay. This particular observation, there was a paper, I think a very important paper. So I have marked with a star and then given a footnote here. So evolution of shrinkage with carbon equivalent and inoculation in ductile cast irons. A paper by Anna. So these are the authors, and they have written a paper on this. And I think it is very important paper, and there are few findings which we will continue to discuss in next slides. Okay. Okay. So now we have understood how ductile iron shrinks. It shrinks in a mushy zone. There is a freezing range. So as that carbon equivalent increases up to 4.3, that freezing range goes on decreasing. The solidification shrinkage goes on decreasing. And then after 4.3, it increases. So now we have understood some information about ductile iron shrinkage. So now the question is, how much is the shrinkage? So since shrinkage is variable, so we can't really say that ductile iron shrinkage is so much because that depends on carbon equivalent. To be more precise, it also depends on your other presence of other materials like silicon, manganese. So when we have all those elements and then we collect data, again experimental data of those particular phases at different temperatures. So whatever carbon equivalent diagram we see, it is a very simple, very primitive phase diagram. But when we add manganese and then silicon and other effect of other alloys, then it becomes a complex phase diagram and it becomes more accurate. So there, I think then our shrinkage we will come to know more accurately. But right now, I think it is enough for us to understand that solidification shrinkage of ductile iron is between 4 to 5%. Okay. Okay, so the paper cited in the last slide, it also found out that excess inoculation also contributes to shrinkage. So now we saw that the chemistry or chemical composition significantly impacts the solidification shrinkage. Now, same paper, when they were carrying out those experiments and collecting data, they also found out that excess inoculation also contributes to shrinkage. So, what it does and how it does, we will look at those things later. But I think it is good to keep it in mind that our inoculation should be optimum. It should not be less, but even more also is not really advisable. So use optimum amount of inoculant in an effective manner. Since we are talking about optimum inoculation, how do we decide whether it is excess or it is less? So I think the best way to go about it is that you see your micros, you see not 1 micro, not 10 micros, not 50 micros, you see hundreds of micros. Every day you take out some few samples. Over a month, you will have seen hundreds of microstructures, and then you will realize that if your inoculation was on the lower side, then you see carbides and then other undesirable phases, and then you realize that yes, uh, you had less inoculation in those hits. So then when you have seen a lot of microstructures and correlated them with the amount of inoculation, you will come to know yourself in your conditions, with your materials, in your furnace, at your pouring or melting temperatures, what is the optimum amount of inoculation. I think this is very important, and everybody should understand what is the optimum amount of inoculation in their foundry, because it changes from foundry to foundry. So you find out what is the optimum amount in your foundry. Okay. Okay. So the difference between shrinkage and contraction. This is something I think uh, very basic, but I think it is important that we discuss this. See, here, this particular graph on y-axis, it is volume, and then on the x-axis, it is temperature. So when you plot a cooling curve, sort of, as the sample cools down, there is a volume change. So this is actually a cooling curve. So as the temperature drops, your volume also drops. So when you see a cooling curve like this, starting at this, so here it is your pouring temperature. So from pouring temperature to your room temperature, or whenever it becomes solid, so you draw that cooling curve, and then what do you see? So here it starts solidifying. Okay. And since our ductile iron solidifies in a freezing range, in a mushy zone, so the solidification occurs in temperature range. There is no single temperature at which it solidifies. It solidifies over a temperature range or a solidification interval. So that interval is like this. So here at this point, it starts solidifying. So this is your liquidus temperature. And here at this point, it solidifies completely. So here it is your solidus temperature. So between these two temperatures, it solidifies. So the solidification, it starts here and then it ends here. So it is here at this point, it is 100% solidified. Okay. So from here to here, it was liquid. From here to here, it is semi-liquid or semi-solid. And then from here onwards, it is completely solid. Okay. So this particular range of temperature, when it cools down, the volume decreases and it is called liquid contraction. Because liquid, when at a higher temperature, will have a higher volume. At a lower temperature, it will have a lower volume. So when it cools down from a higher temperature to lower temperature, only the volume of liquid has reduced, and that is called liquid contraction. Okay. From here to here, now it is solidifying, and then since it solidifies in a temperature range, so there is a temperature range or solidification interval, and then from here to here, we can see there is a decrease in volume, and this volume is basically called solidification shrinkage, as we have seen earlier. The difference between liquid volume and the difference between liquid volume and solid volume is called solidification shrinkage, and that you can see here. Now, what happens after solidifying? It is still at a higher temperature, and when it solidifies to your room temperature, volume again comes down. Now, this we all know, and we call it as solidification contraction. So this we compensate by adding contraction allowance in your patterns. Pattern shop.
Has done extremely well. आज भी अगर आप SBI को देखें, the valuations are not demanding at all. I think at 1.7, 1.6, 1.7 price.
Okay. Okay. So at here, this particular reduction in volume we compensate by adding a contraction allowance in the patterns. So when the patterns have been designed with an appropriate, accurate contraction allowance, then this particular volume decrease has been fully compensated. So we get our casting to the dimensions which are desired by the drawing. So this particular part we take action, we resolve this particular volume contraction. Here, this is only a liquid volume change, so it really doesn't impact our solidification shrinkage. So our actions are basically coming down to avoiding this particular shrinkage. Okay. So how do we compensate this particular reduction in volume when it solidifies over a temperature? Okay. Same picture, but here we have a different way of presentation. Here, this is temperature, and here it is time. So it is not volume, it is time. So as temperature decreases over time, so the curve comes like down like this, then it goes like this, then it goes like this, then it goes up again. So there is a increase in temperature at this point of time, and then it plateaus, then it comes down again. So this is how from here to here it cools down. So the same thing when we see on the phase diagram. So you can see the material is cooling down like this. So this cooling down is basically what we see here. Okay. So the point 1 is the point 1 here. Point 2, 3, 4, all these points are here. 2, 3, 4. Okay. So this is your liquidus point, and at this point solidification starts. So at this point solidification starts. That is why the temperature is decreasing over time, and as the time increases, temperature is decreasing. Then at point 5 here, there is a slight increase in temperature as well. All that liquid suddenly solidifies, and that particular phase reaction contributes to a slight increase in temperature, and then that is why the temperature from 0.5 to 0.6. So this is 0.5, and then 0.6 is below. So as it moves from this to this over time, temperature slightly increases, and then at 0.6 it starts plateauing down, it becomes constant, and then it starts decreasing. So this is what happens when a particular casting is solidifying, particular casting of a given composition is solidifying. So what are the phases here? The first phase is 100% liquid. So at point 1, you see it is 100% liquid. Okay. This yellow between point 2 to point 4, it is yellow. So what is that yellow? It is liquidus temperature area. So it is coming down up to here. It is liquid. So the phase is purely liquid. And at point 4 now it starts becoming solid. So what is that red phase? It is austenite plus liquid. So here it is that again that mushy zone. So there is a part of it is liquid and part of it is austenite solid. Then at point 5 it is completely solid. So that is the first eutectic area. And here now you have your austenite and your cementite or other phases depending upon your chemical composition, whatever it is. Then this is when it comes down below the another temperature, and then this is called your second eutectic area, and then here onward it becomes completely solid. So these are the phases when the material is cooling down from like this, or if you see like this. So what is the lesson or what is the information we are trying to understand from this? The eutectic graphite. So when the phase reaction starts here, when the liquid starts, when austenite starts solidifying here, few flakes, few grains have come out. They have started solidifying, and then as we move like this down, more and more austenite starts for solidifying, forming, and the liquid volume comes down. Austenite volume increases. So when austenite starts forming, there is another reaction which is also happening, and that is the eutectic graphite, which is dissolved in the liquid. Now it starts precipitating. Okay, so I think here I would just like to mention briefly, because if we try to understand the graphite precipitation, it would take a long time. Usually when we discuss metallurgy as a central theme, then I discuss those points in more detail. But briefly, what I would like to mention here is that the solubility of graphite is much more in liquid than it is in solid. So when the liquid starts solidifying, the solubility of graphite is decreasing. So when solubility decreases, what happens to the graphite? It has to come out. Correct? Just imagine that there is a glass of water and you have added salt to it, and then at certain point of time, the salt doesn't dissolve and it remains in water. Then you heat the water, and then that whatever that salt was there, it also dissolves. Then you cool the water, then that excess salt, it again comes out. So similarly, when salt solubility was high in hot water, but low in room temperature at lower temperature, so that excess salt precipitated. So similarly, the excess graphite which is dissolved in the liquid, and when that liquid becomes solid, that excess graphite has to come out. And this is very interesting. That excess graphite is what is helping us to take action on the shrinkage, solidification, shrinkage, and that is what we are going to discuss. So what happens when this graphite comes out? Okay, first thing what we look at it is how much graphite actually will come out, because that is very important. More the graphite that comes out, more it becomes beneficial for us to take action on the solidification shrinkage. So this is a very important point. So that is why I think this information is very important, that we have to understand that when ductile iron or grey cast iron, it solidifies in a mushy zone or a freezing range, graphite comes out. And graphite, because graphite comes out, uh, there is a associated impact on the volume of the liquid, which we are going to discuss. But right now, at this point of time, we just want to understand that how much graphite will come out. So here there is a formula. This formula is here, that eutectic graphite is there is a percentage of carbon, and then there is a percentage of silicon also involved. So when you this is a simple formula again. And then if you want to add effect of manganese and other elements, it will slightly change. Not much, but slightly change. So more accurately, almost confidently, you can use this formula to understand the amount of eutectic graphite which is expected to come out during solidification. So just an example, if your carbon is 3.8% and your silicon is 2%, then your eutectic graphite is about 2%. So just imagine 2% of graphite is going to come out during solidification. Okay. So why this amount of eutectic graphite is important? Because when graphite was dissolved in liquid cast iron, the density of cast iron is 6.9 grams per centimeter. The density of graphite is 2.2 grams per centimeter. So when the graphite comes out and the liquid density of liquid cast iron slightly increases, but graphite, since now its density is very low, so it is going to expand, because now graphite is going to come out. 2% of graphite, when it comes out, it expands the volume of the liquid. And how much is the expansion? For this particular case, I have calculated. And when carbon is 3.8%, silicon is 2%, your eutectic graphite is 2%. When all that eutectic graphite precipitates, it will expand, it will increase the volume of the liquid by 6.2%. So just understand that the solidification shrinkage is between 4 to 5%, but the effect of graphite expansion, graphite precipitation is 6%. So when your graphite precipitates fully, nicely, accurately, soundly, then this graphite expansion can fully control or eliminate your shrinkage, solidification shrinkage. So that is the learning point. That is what the takeaway from this particular slide. And we can all work out how much is the expansion, and whether this expansion can help us to counter solidification shrinkage in our casting. Okay. But here I think the most important point is that when graphite precipitates, the volume of liquid increases, and if our inoculation and our melt quality, our processes are correct, then all this expansion is available. The benefit of this expansion is available, and then we can nicely, in a very structured manner, control our solidification shrinkage. So that is the point which I want to make here. So, but this expansion will not be available if our melt quality is not right. So this is how the link or the impact of melt quality on shrinkage defects in ductile iron. So this is the basis of the whole idea of the whole discussion today. Okay. Okay. So in this slide, I have just given some references from literature, the solidification, volumetric solidification shrinkage. So the table on the left side, it gives volume of solidification shrinkage for different cast metals. For aluminum, it is 6.1. For zinc, it is 6.5. Sorry, aluminum, it is 7.1. Zinc, 6.5. Aluminum, copper, 6.3. Gold is 5.5. White iron is between 4 to 5.5. Copper is 4.9, brass is 4.5 again. Magnesium is the new metal. Many foundries are now trying to develop magnesium castings. So magnesium again is 4.2. Copper alloys 4. Carbon steels 2.45 to 4%. lead is 3.2%. And these are the rare exceptions to this particular here. Here it doesn't contract. There is an expansion. So bismuth expands, silicon expands, gray iron expands. So this is an expansion data. There is another reference from another uh, site, solidification shrinkage of different materials. So aluminum 6.6, copper 4.9, magnesium is 4, zinc 3.7, low carbon steel 2.5 to 3, high carbon steel 4, things like that. So scientific data for solidification shrinkage is not identical everywhere. So that is what I think I would like to mention. But it is fairly in the range of 4 to 5%. And that is what I think we should understand, keep it in mind and move ahead. Okay. Another interesting slide. Some examples of shrinkage defect. So many of these photos I have personally taken. So here you can see a neck shrinkage. This is quite common defect in ductile iron. Then below there is another neck shrinkage. It is exactly on the ingate or the riser neck. So there is no doubt that this is a neck shrinkage. Then in some, this is the shrinkage appears in a core zone. So now why it happens in core zone is another, I think we will take it up in the next webinar when we specifically discuss about defects and their mechanism. But here, only I think I would like to mention is that core zones, when casting geometries are in such a way that the the core is thin and the casting sections are thick. So such geometries and such part designs are quite prone to shrinkages in core zone, impellers, for example. Then here there is a shrinkage in a hotspot. So there is a section like this, and you can see another junction here. So a thin section is joined with a thicker section. So this becomes a hotspot, and the shrinkage has exactly appeared in the hotspot. Another hotspot here. So these are predictable behavior of shrinkage, and so when your defects appear in this, most likely, most certain, with certainty, you can call them that these are shrinkage defects without being misled by appearance or other factors. So these are the shrinkage defects. You know, you can see the appearance of shrinkage defects are different. Here it is a big defect, whereas here these are only small pinhole sort of defects. Another very common defect is when we make drills. We drill and then inside we find porosity, very small defect. So you can see defect here, and also you can see inside the bore there is a defect. So these are the shrinkage images, and they differ quite a lot. So it is important that we identify the defect correctly. Most of the times, the location of the defect helps us to identify the defect correctly. But if we don't identify defect, because in some cases, a slag defect can also appear like a shrinkage defect. Here, I would like to mention this just passingly, briefly, that in one foundry, we struggled with defects in one particular cylinder head for a very long time, took many iterations, many trials, and our customer was facing heavy rejection after machining because these defects were revealed only after machining and during pressure test. And he was suffering from high rejection after machining and during pressure test. And since it was happening in a bore, and we thought that it was a shrinkage, and we were taking action on shrinkage, and it really didn't respond. So another important aspect of defect analysis and our corrective action is that when your defect doesn't respond to your corrective action, then that means that either your corrective action was not in the right direction or your identification was not right. So if you have a throat problem and your doctor gives you medicine for your digestion, so naturally those pills will not uh, so your throat infection and sore throat will not respond to those tablets. And then you have to understand that his diagnosis was not correct. So most of us, we see that our corrective actions, our defects don't respond to our corrective action. And then you have to understand that the casting is telling us that please go back, revisit your investigation, relook at the data and identify or take action more accurately, more effectively. So, so just sharing one experience that defects, because they look alike, sometimes we can get misled and then it prolongs our time for taking corrective action. So method to overcome the shrinkage. Now, this is very important. So it is possible to completely compensate the shrinkage and produce shrinkage-free casting because there is an expansion. So when we do things correctly, so it is possible to compensate the shrinkage, or to a large extent we can compensate the shrinkage because there are different sections. So this statement is technically correct if there are no complexities of design, thin sections, thick sections, section changes. So that makes the shrinkage behavior complex and unpredictable. But in simple shapes, it is completely possible to compensate the shrinkage by this expansion and then produce shrinkage-free castings. So when we are doing work for steel casting, the method is then the identify the hotspot of the casting, then calculate the casting modulus of the hotspot. The casting modulus is a mathematical procedure for finding out which section of the casting will solidify last, and then it directs us to give a feeder at that particular hotspot so that the feeder will completely compensate the solidification shrinkage and you get casting which is free from shrinkage defect. And then the third stage is that calculate the riser neck or the riser shape. So this depends upon the molding process and the casting geometry. So for materials like steel, stainless steel, aluminum, bronze, or copper alloys, I think this is a fairly structured method and fairly, I would say, uh, effective method. It has a basis, mathematical basis. So if you are using simulation softwares or simulation tools or modulus calculator, you can do this work very correctly. You can calculate the modulus of the hotspot. Then you decide the modulus of the riser, then you select geometry depending upon the casting geometry. You can decide the geometry of the riser. Then based on the particular modulus of the riser, you can choose a particular sleeve or the riser very accurately, very confidently, and then decide your riser neck, and that's all. So if your casting modulus is 1.0, then you have a riser neck of modulus of 1.1 and have a riser or sleeve of modulus 1.2, and then it takes care of. So it's very simple. So that is the benefit when you are working with obedient materials like steel and copper alloys. But for ductile iron, there is a difference. So because ductile iron uh, expands and so it behaves in a different way. Each casting behaves differently. Each part behaves differently. So even if you are pouring same metal into two different molds of two different casting geometries, there will be a difference in the way the shrinkage is happening. So it is a complex process. So for ductile iron, at this particular point, we understand that ductile iron behaves differently. So we have to work on ductile iron in a different way. Before we move to next slide, I think it is worth mentioning that there is a class of castings in ductile iron which does not need feeders. So I think when I was young and I started my career and we heard about some foundries in South India, maybe it could be Mysore Kirloskar also, I am not really sure, but I just heard that they were making casting, very large casting, and they had hardly very small feeders. So almost riserless feeders. So I think this is correct. So based on what I have heard, and I think even the papers say like that, that it is possible to make castings without feeder, but there is it happens under certain conditions. So I think when we talk about uh, specifically about designing feeders in ductile iron at some other point of time, we'll come back to this. But right now, you can just understand because we want to emphasize that but ductile iron behaves very differently. So if you understand the behavior of ductile iron, then we can work on ductile iron more efficiently, more effectively, more successfully. So that is the whole point of mentioning this particular property here. Okay. Okay. So continuing the discussion on casting modulus. So casting does not have one modulus. So let us be clear about it. That if you have a part like diff hub, complex geometry, then it does not have a single modulus. It has several moduli. And then we select a part, a particular area where the modulus is highest, because that is the part which is going to solidify last. And then that is indicated by the highest modulus in that particular area or that particular zone. So the concept, so I'll just read the slide here. The concept of modulus came up from the need of estimating casting solidification time. So what is modulus? Modulus is basically an estimation of casting solidification. So when modulus is higher, the casting takes more time to solidify. And that is what we want. So when casting is solidifying, we want a feeder on the top of the casting, which is solidifying after the casting solidifies, so that it is in liquid state and then it supplies a liquid metal to the uh, area of casting, which is solidifying, which is shrinking, and then it is compensating that shrinkage. So to do that work, it must have a higher modulus. So it must so in other words, it must solidify later than the casting. So how much later? So that is what we apply a 20% factor when designing modulus of riser. So if casting has a modulus of 1.0, we select modulus of riser as 1.2. So that gives us sufficient time for the feeder to compensate all the solidification shrinkage of the casting, provided the riser neck has a modulus of 1.1. Okay. So how do we calculate modulus? It is again simple. So we'll just touch this briefly. Most of you must already be aware of it, but some of the members, the young members, so for their benefit, we'll spend a few minutes on this. So when we look at this particular geometry, this is very simple geometry. There is section A and section B, and there's a joint here. So we can see that section B is much heavy, section A is thin section, and section A will surely solidify much earlier than section B. So how do we quantify this? So now since we are saying that modulus is same thing as solidification time. So what we are saying that section modulus of section A will be much less than modulus of section B. So we need to identify how to calculate the modulus. And then once we calculate, we know that modulus of section B is more than modulus of section A. So we have to feed section B. So this is the understanding when we calculate modulus. Many in their working terminology called MB as the significant modulus, because that is where we have to take action. We have to design riser. So that is the significant modulus. It is affecting our process of metering. So what is modulus? Modulus is simply the ratio of volume and the surface area of a section. The volume stands for the amount of heat present in the section. So why volume is important? Because volume contains all the heat in that particular section. So we have to remove the heat from that section, and that heat will go only through the area of the section. Correct. So surface area of the section decides the cooling rate, and the volume of the section decides the amount of heat to be extracted. So that is why the modulus of this section is the ratio of the volume of the section and the surface area of the section. Clear? Very simple. So we have to extract heat from a volume of a section through the surface area of the section. So we divide the volume by the surface area. So we get an idea of the solidification time, and that ratio is called modulus of the section. So volume is A into, for this particular our case. So volume is A, that is the length, B is the width, and T is the thickness. So the volume is A into B into T, surface area. So surface area of this particular is 2 times A into B, then B into T, and A into T. So this is the surface area. Now the common phase with section A is not a cooling phase. See, so when section A is connected to section B, so this particular surface contact area is not really cooling. So we reduce this area from the cooling area. So the cooling area is surface area. This is the cooling area. So we minus this particular area, which is C into T. C is the thickness of this or width of this, and T is the thickness. So C into T is the area which is common. So this is not a this is non-cooling area. So we reduce this from the total cooling area. So our modulus is A into B into T divided by the surface area minus the non-cooling area. Clear? So all this is mathematical, and we just understand the idea of modulus calculation, why it is to be calculated, how it is calculated, volume divided by surface area, the cooling area has to be minus. So once we understand this, there are now calculators. There are simulation softwares which talk about modulus, and they readily calculate the modulus. And then when you feed the casting drawing, then they immediately calculate the modulus of each section and then show it to you, so that when you feed your drawing into those software, you can just look at the drawing, you can look at the 3D picture and see this particular section has highest modulus, and then you understand that that is the hotspot, and then you have to take action on that. Okay. So here again, I have just explained the formula of the modulus. So when a section is like this, so modulus is A into B divided by 2 times A plus B and minus C. C is this area. Okay. So this is the formula, and there are many more formulas. So you can get those formulas and use those formulas to calculate modulus yourself, understand how it is calculated, and then get a more comfortable, confident feel about modulus calculation. So this is, I think, an interesting idea of what happens during expansion. So here this is the section, and we have attached one riser here, side riser here, and then the whole thing is now filled, and then it starts solidifying, and there is a liquid contraction. So this white is liquid contraction, and then now this is going to solidify, and then this whole thing is going to compensate, and then there is an expansion. So this whole thing, then this expands. So the liquid which is present here expands while this is still liquid, and then it pushes the whole thing upwards. So this again becomes full. So you see, it was contracting, and then during solidification, then it has again completely filled this. So I think there is a very important statement which I read recently. In ductile iron, the pressure is important. The metal pressure is important rather than the volume is important. So what is the pressure? The pressure is here. So when it is expanding, the whole thing it presses. The pressure of expansion pushes the metal again back into the riser. So so when the riser and the riser neck is correctly calculated, so this expansion fully compensates your shrinkage. So this is called pressure control risering, and uh, this is the mechanism how ductile ion solidification works, how it compensates shrinkage. So in most cases, we are very lucky that this mechanism is available. And so unlike steel, the risers of ductile ion can compensate much more than a normal steel riser would have fed. Their the freezing, sorry, the feeding range is also more than what traditionally a steel casting feeds. And some time back when I had uh, wrote a paper on this, and it was published by IF Kolkata in the Indian Foundry Journal. And many scientific papers also give citation to this particular observation, my observation, which I had mentioned in the technical paper, that ductile iron helps you in giving you a more feeding range than a steel casting. That is because there is a benefit of expansion. So once we understand that ductile iron helps us by from its graphite precipitation and related expansion, we take benefit of this in designing our feeders, our methoding, ap- select appropriate size feeders, appropriate size riser neck. Riser neck is more important. And then when we have done like this, and then there is a very good chance that our methoding will give you castings which are free from shrinkage. Why I'm saying good chance? Because initially, when you are developing, you have good conditions, you make samples, you get good casting, then you make hundreds of casting. Those are all proven. It validates your methoding, that methoding is taking uh, uh, is compensating the solidification shrinkage fully, and then you confidently go ahead and start bulk production, and then you again run into a problem which I had cited earlier in the beginning of our training. So then at that point of time, we have to realize that something somewhere our melting controls have not been there fully. Somewhere the melt quality deteriorated, and then that contributed to shrinkage. And then so we don't have to act on the methoding, we have to act on the melt quality. So where did we go wrong? What did happen? So we have to identify the areas where our melt quality contributed to shrinkage. So how does melt quality contribute to shrinkage? So I think we'll come back. So that is the part now which we are going to look at. Okay, so some basic points. Riser should be as close to the casting as possible. Riser modulus may be same or slightly more than casting modulus. This is relevant to ductile iron, not relevant to steel or aluminum bronze or copper alloys. They strictly they want riser modulus to be 1.2 times casting modulus. If it is less, then in some cases they will show their disapproval by showing you casting defects in critical section. So, but since we are getting a benefit of expansion in ductile iron, So it may not be really 1.2 times, but I think on safer side, it is a good practice to maintain casting modulus in ductile iron also has 1.2 times casting modulus. But I'm just mentioning here that it may be slightly less sometimes. Neck contact modulus may be about 0.5 to 0.6 times casting modulus. This is, I think, the most important point, that unlike in steel, where the neck modulus is 1.1 times casting modulus, if we give the same neck modulus in ductile iron, it will contribute to neck shrinkage, because we now go back to earlier. So here, when this is about to solidify and about to expand, the expansion, if at the point of expansion, if this neck is not frozen, not solidified, then all that expansion will push the liquid metal into the riser. And then when the solidification really starts, this neck solidifies, and then this riser will not be able to compensate the uh, shrinkage which is occurring inside, because the neck has, sorry, the neck is still semi-liquid. So the riser feeds the liquid metal because it is not yet has not yet become solid. So it feeds the solidification shrinkage, and then at some certain point of time, if the expansion has not been sufficient, so there will be a shrinkage. So that will happen because the riser, this particular gate was not closed early. The critical idea of designing riser neck in ductile irons is that this should freeze early. So when this freezes early, it doesn't allow the expansion and the subsequent liquid metal to get into riser. So when it doesn't allow, so that whole expansion then compensate the solidification shrinkage which is happening in the casting. So that is the point. So the neck has to solidify early so that the expansion doesn't allow liquid metal to flow into riser, and then it compensates the solidification shrinkage which is happening in the casting. So this is the point which I think I'm trying to make clear here. So for that particular process to happen, the neck modulus should not be more than 0.6 or 0.7 times casting modulus. When neck modulus is higher, then there are quite chances that the neck will not freeze in time, and it will allow the expansion and the subsequent metal going into the riser. And then when the solidification is getting completed, it solidifies and then doesn't allow the riser to fully compensate the shrinkage. So the neck modulus, if we keep the neck modulus of the correct size, correct modulus of correct design, then we are able to take the benefit of the graphitic expansion fully, and then we are able to compensate the solidification shrinkage in casting sections fully. So I think this point is worth repeating again and again, that neck modulus should not be or should be in the range of 0.5 to 0.6, sometimes 0.7 also. But more neck modulus, and we run into the risk of neck shrinkage. The fourth point is gross shrinkage cavity in riser indicates that either the riser is too small or the neck is too small. So this happens in the case of steel casting most of the times. A carbon equivalent between 4.35 to 4.60 is good for getting the expansion benefit. Yes, because more graphite is available, and so But as we have seen earlier, as the carbon equivalent increases, the solidification shrinkage also increases. So we have to do a balance, and maybe carbon equivalent close to 4.35 is, I would say, an optimum carbon equivalent where you get the benefit of fluidity as well as lower solidification shrinkage. Low holding time. So why holding time is important is because that is the most critical parameter, the condition which affects the melt quality. I think this is something which many of us uh, have not are not fully aware or seriously aware, because holding time is something where a well-made melt gets deteriorated. So when does holding occur? So when your molds are not ready, you are waiting. You have first spectral sample asked for some additions. We made those additions, then send back the sample. That's the second sample result is coming, and we are holding the furnace. So you analyze your holding conditions, your holding practice, your holding time, and then you realize that yes, there is a lot of holding, and then whenever there is a holding much beyond certain time, your melt quality gets affected, and then you not only get shrinkage defect, you also get some other defects. Holding increases your liquid slag in the metal, and when you do inoculation, you do treatment, your liquid slag also gets reacted with the inoculant or the treatment alloy, and then it reduces the effectiveness of inoculation or treatment. So holding is a major killer of casting quality, a major influencer as far as casting shrinkage defects are concerned in ductile iron. Inoculation must be effective, no doubt about it, because your all your graphite precipitation volume depends on how much you inoculate. So if inoculation is less, then you get lesser graphite, lesser expansion. If inoculation is more, your graphite volume will be more, expansion volume will be more. But then in after a certain point, you also run into shrinkage risk, as it was mentioned by the paper, which we saw earlier in the slide. So don't be on the lesser side, be on the slightly on the higher side, but don't go overboard. Find out what's wrong with your inoculation. Most of the time, you choose very good inoculants, you do inoculation, but since the inoculation was not done correctly, so your inoculation quantity becomes inadequate, and then you run into problem of carbides. Then you start introducing mold stream inoculation, but you still continue to get problem. I have seen this. I have seen this in one very good foundry where they were doing mold stream inoculation, and they had 30% cases of carbides. So they were using best inoculant. They were doing using inoculant feeder, which was attached to uh, their pouring station. So with all that in place, still they were getting high amount of carbides in their casting. And when we took action, the action was that the inoculation feeder was delayed by a couple of seconds. So it was feeding inoculant into the metal a bit late, and then the initial metal which was not collecting inoculant, and then it was not really giving the benefit of inoculation, and then whenever that particular initial metal went, it showed carbides. So I'm just giving this particular my own experience that inoculation to be effective is not only choosing right inoculant, right seed or particle distribution, but how we add inoculant. My own experience is that if we do inoculation perfectly, no mold stem inoculation is required. If you require mold stem inoculation, that means somewhere in the initial stage is something needs correction, something needs your attention, and when you do that, then you get excellent benefit of inoculation, and probably no cases of carbides or other impacts of bad inoculation or inadequate inoculation. So inoculation must be effective not only for avoiding your machining problems, your other problems, but most importantly, your graphite expansion. So if your inoculation is ineffective, your graphite precipitation will be inadequate, and then it will not compensate your shrinkage fully, and then you run a risk of shrinkage defect. So that is why inoculation is important. And since inoculation is related to melt quality, so again, we are coming back. Holding time, inoculation. So these are the factors which decide your melt quality. And then this impact your shrinkage defect. So now we are slowly understanding how melt quality affects your shrinkage defects. Correct? Limit the carbide forming elements. Okay, so this is just a theoretical statement. Sometimes we have to pour with this element, this chemistry, and then we have to take suitable action. But yes, as far as possible, like for example, chromium. So you can avoid or reduce the chromium amount if you buy suitably uh, deciding your carbon equivalent. So if you decide your carbon equivalent on the lower side up to 260 grade in gray cast iron, you don't need copper or chromium. So you can make a 260 FG260 grade with all tensile and then maybe hardness requirements. You can fully comply with those with very low amounts of carbon, with low amounts of chromium. So as far as possible, you can avoid these carbide forming elements by choosing your selectively choosing your carbon equivalent. Okay. This is another very important chart. So here again, specific volume versus temperature. So as the sample is cooling down, so you can see your there's a ATAS. So I think some of the foundries must have installed this ATAS equipment. And then when you pour a sample, then it gives you cooling curves. And then when your cooling curve is like this is your base cooling curve. So when your cooling curve is like this, then you have minimum risk of shrinkage defects in your casting. So if your cooling curve is like this, then you have very low risk, very low probability of low. Hello. 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 I think what we can do is whoever has got some questions, we'll have a question and answer session. I think we have very few slides now remaining. So I'll just quickly complete this. But this is an important slide, which is very relevant to the today's theme of how melt quality affects shrinkage defect. So here you can perfectly see. So when your melt quality is good, so your ATAS will show a cooling curve like this. When your melt quality is bad, so your ATAS will show a cooling curve like this. So you yourself can see that your melt quality is not good. Your ATAS equipment will show you cooling behavior, and it gives you alert that something is wrong. So either you correct or take some action and then pour. So we should aim for getting cooling curves like this and avoid cooling curves like this. So I think, to be honest, to be frank, I think most of the good foundries which have good controls in their melting section, their pouring section, their press pour setup, their molding lines, they have good coordination, they have an inoculant feeder. Sometimes they also use mold stream inoculation. So with all that, I think most of the foundries are running, or when they show when they see their cooling curve, I think they will probably be in this range or between A and B. Sometimes they will get into the C, which initially when I was talking about my experience in Aisha. So I think this is what happened. And since we were not aware at that time, so we did not look at what went wrong in our melting, but we continued taking trials on molding sand and then our metal. So melt quality is what you can see here. So you should aim for melt quality of cooling curve A, avoid melt quality of C. If you are in melt quality B, then you understand what is preventing you from going to melt quality A. Take those actions, exercise those control so that you will remain close to melt quality A. And when you remain close to melt quality A, your castings will have very low risks of shrinkage defect. So that is how your melt quality and shrinkage defects are linked. Okay, so now then naturally you will ask me what we should control. So the first control is charges. Please use clean, rust-free, oil-free charges because if you are melting rusty charges, then you are already adding liquid slag into your melt and it is going to exacerbate, it is going to aggravate, it is going to increase your risk of shrinkage defects in your casting. So this is very important. So because this is something which is definitely in your hand. If there is a rusty charge, then you can control getting it melted. You can control getting it clean, ensure that it is rust free, and then only add. So this is something very much in your hand, and you should do that. Melting time. So melting time should be as low as possible. Melting time and your melt quality are very much related, and more is your melting time, then less is or your melt quality suffers. So when your melting time is very high, then you understand that yes, something must have gone wrong. I don't know what has gone wrong, but I must take some action on my melt quality. So melting time is another thing which will give you an alert, which will be like a buzzer that yes, now you are right, you have melted in correct time. So please don't worry and go ahead. But if your melting time was long, then something was wrong, something needs to be taken action, see what is wrong and then take action. Slag removal. So what we do is we remove uh, furnace slag, which is floating on top of the liquid metal. But slag also exists in many other places and it escapes our attention. So what we see actually physically is only a solid slag. But slag is basically a mixture of oxides. So when we have manganese, chromium, silicon, and some other elements in our metal, so you will see oxides of silicon, you will see oxides of manganese, chromium, and this depending upon if it is a ferrous oxide or silicon oxide or chromium oxide, they have their own melting points, and ferrous oxides, they have their melting points lower than the melting point of liquid metal. So, so liquid slag, which is more liquid than more fluid than the metal, is difficult to trap. So this is where I think the liquid slag, if our gating system is not designed, our pouring practice is not designed to trap liquid slag, if our melting practice is not uh, mm, focused on preventing liquid slag formation, then there will be some liquid slag and then it will easily bypass your filters. And if there are no slag traps in your gating system, then it will also enter casting. And then depending upon your casting geometry, it will exhibit casting defect, or it will simply, if you are lucky, it will float into your riser. So sometimes the liquid slag, which is it has remained in the ladle, it then sticks to your ladle lining, your spout, and then when you are melting next time, pouring next time, this liquid slag again melts and then again goes into casting. Multiple tapping. The best quality metal is when the first tap. So if you are able to tap all of your metal into a ladle in a single tap, that gives you the best quality of liquid metal. But if there are multiple taps, then you understand that the first ladle which goes and then comes back, then during that time your metal is under hold, and then so the melt quality slightly deteriorates. So as far as possible, uh, go for first tap, one single tap. If you are not able to do that, try to minimize your taps by taking actions on other places where you can probably use a higher capacity ladle, do some multi-cavity metering, something so that you are able to tap your reduce your taps, and then that gives you best benefit of your melt quality. So when you have melted best quality of charge, you have taken sufficient care to melt it in minimum time. And then if you are doing multiple tapping, then naturally your quality deteriorates and then your risk of shrinkage defect increases. Lastly, pouring temperature. Higher the pouring temperature, then higher will be the solubility, the liquid metal, liquid slag formation. So as far as possible, tap or tap at a temperature which is optimum. So if you want a certain temperature, okay, go for it, take care, but don't exercise control so that you don't cross it. So for example, if your control plan says that you will tap at say 1560 degrees centigrade. Okay, because you are pouring some particular casting which have thin sections and you want your pouring temperature at the mold spout to be something like 1420, 1450. So you choose your tapping temperature about 1550, 1560. But then you see that it doesn't exceed 1560. It doesn't become 1570, 1580. Because if it goes 1570, 1580, then you know that the liquid slag must have formed more, and then you run into quality risk. So pouring temperature is another control point in your hand, which you can control rigidly, strictly, and maintain your controls on melt quality. Okay? So these are the 5 points which we discuss, which impact your melt quality. Composition. So, okay, composition is something which is not really in your hand, because we are making a particular grade. We have to deliver certain properties. We have to show these properties in our casting, tensile in our test bar, hardness on our casting. So we really have not much of a choice. But as far as possible, go for something which gives you less. Uh, Less chances of getting those liquid slag and then melt quality, affecting melt quality. So there's a little area, little window here which you can control, but not big. But I think all the earlier points which we discussed just now, you have a good amount of window there, and I think you should exercise control in that window. Pouring, I think mechanized pouring is best, because manual pouring, it will have some variability, and then whenever things are there is a variability, then something definitely happens. So quality variability is the biggest enemy of quality. So if something is variable, then we are inviting some quality risk. So mechanized pouring is best as far as melt quality is concerned. Pouring speed, fill the mold as quickly as possible. If you are taking more time, then we are exposing the liquid metal imagine the metal is falling in air, and then since it is at higher temperature, it is attracting oxygen at a higher rate. So if you are pouring at a longer for a longer time than necessary, then you are increasing the formation, the liquid slag formation, oxide formation. So pouring speed is another important parameter. Ladle insulation. If ladle top is not covered, here what I mean is by insulation from the top, because that is the area where your temperature loss is highest. So if you are doing something about that insulation, controlling temperature loss from the top, then you are ensuring that your molds get poured at a consistent temperature, consistent fluidity, because if fluidity drops, then you again run into risks of shrinkage and other defects. So ladle insulation is another. I think most of the foundries are doing it now, but just highlighting here because it is relevant and it is very, very relevant. Stream inoculation. My own experience is that if primary inoculation is done in the right manner, you don't need stream inoculation. But okay, you can add it to add some comfort factor to ensure that your process remains robust. So a small amount, I think you can add. So whenever you decide to do stream inoculation, don't do excess, because we see that excess inoculation contributes to risk, shrinkage risk become higher when inoculation is higher. Mold clamping. This is oftenly overlooked, but if your mold clamps are not inadequate, then your expansion benefit gets reduced. Correct? So mold clamping is important because it impacts it affects your expansion benefit. Okay. So here, why I am showing this is air aspiration. So this is something, there is a glass vessel and then water is rising and you can see air bubbles here. So this is what happens when pouring is turbulent. The flow is turbulent. And when there is a turbulent flow, there are air bubbles. So air bubbles are basically if your water is catching air and then creating air bubbles, imagine what your liquid metal will do. So liquid metal will also catch air bubbles. And then when these air bubbles go inside, the popularly the Campbell theory basically talks about these air bubbles or biofilm. So this creates the source of the microporosity and pinhole porosity in our casting in these air bubbles. So these are again related to your melt quality because you have taken all those actions, safeguards, your pour casting, but during your pouring, there is a violent turbulent flow, and then your metal gets oxidized, reoxidation. So that is called reoxidation, air entrapment, and then it creates a risk of defects, and these are more harmful because these defects lie subsurface and these are opened after machining. So these are more harmful than your other defects. So what we should do in gating, and so these are roughly some small guidelines. So the runner is in drag. So what happens that when your metal runs into runner and runner is in drag, so the slag, there is a high chance of the slag going into the casting. But if you keep the runner in cope, the slag floats in the cope, and there is a high chance that the slag will get trapped in the runner. So the runner is in drag is something which we should try to avoid. Still better. This is a poor practice. A casting is designed like this. So why this is poor? Because when here the metal will run like this, here the metal will run like this, and there is a good amount of possibility that metal fronts collide against each other. And when metal fronts collide against each other, there is a turbulence, and then, as we discussed in earlier slide, air bubbles and all those unavoidable entities get formed. Get runner. So this is okay. This is something we do. Runner. The ingot is here. This is runner, and the slag floats to the top. But why this is shown poor? Because you could do. You could design like this. A tall runner will trap slag better than a thin runner or not tall runner. So this is something a small design factor here, design idea here, which we implement. I think it will also make your process more robust. Good practices. So this is a poor practice. So why this is poor practice? Because we have attached uh, a runner into riser. So this makes the riser a hot riser. Traditionally, this is called hot riser. But why this is poor design? Because in many cases, what happens is that the riser neck is designed for a cold riser, and when you add a runner into the riser, so it actually increases the uh, time a riser remains in solid state, in liquid state. So when the riser remains in liquid state for longer time, then it also affects your riser neck. So the riser neck, when you had calculated as something zero point 0.6 times casting modulus or zero point 0.7 times casting modulus, but then it changes because now we have made the riser hot by adding runner into it. So the good practice or the safer practice is to go like this. So this remains consistent. So whenever you pour, the riser behaves consistently. So this is something, a small factor, small, many times people do this. I have also done this, but then you have to understand the risk. So when you understand the risk and do this, then I think we take more. So when you are running, you are attaching a runner into a riser, then you have to work on the riser neck. So if you do the riser neck alteration, when you attach a runner into riser, then I think you have taken care of the risk, and then you can continue working like that. So this is another point, I think, important point. Contact area. So we all do this. A runner is in the top, and then there is a down sprue here, and then we place a filter here. There is a sprue head. The metal falls through filter, gets collected in the sprue head, and then flows into runner. And this contact area is less, and then so effectively it reduces the flow in your runner. So this is something invisible. We don't really look into this. So at the point of new product development, I think this is something which you must make a point. You must make a note that this is as per your design. This is not something which you had designed but not implemented, not executed correctly. So this, I think, should go into your check sheet in the new NPD check sheet. Slack track. So slack track, this is slack. We all know that runner extension is required, but many times people don't give runner extension. So runner extension, what it does is when initial metal flows like this, the liquid slag or the front, liquid front or the metal front, which is highly oxidized, which collects air, entrapment, air bubbles. So the initial metal is actually something which has liquid slag, entrapped air, and other things, maybe some eroded sand also. So if we are designing our runner in such a way that the initial metal is trapped by giving an extension and then adding an slack track at the end of the, then this becomes a completely foolproof, fail-proof system, so that when your metal flows into the casting, you have already trapped your liquid slag, you have trapped the eroded sand, and then there is a good amount of possibility that your castings show freedom from these defects of poor made quality. Okay, so I think we have run quite a lot. I think there is but I think we'll just invite questions, and maybe I'll try to answer those questions. So I think we'll call this at the end of the presentation, and please go ahead with your questions.
So, thank you, sir. Actually, audience, if you have any questions, actually, please, you can raise your questions to Mr. Dhumane, sir. Sir, there are few in the chat box.
Chat box, okay.
Yeah.
So,
What is the root
so
cause?
one
What is the
one
root
minute,
cause of the
one
neck
one more,
1 minute?
1 minute, yes, yes.
Yeah.
Chat, okay. So let me open the chat. Okay, okay. Sir, Mr. Prathamesh, he has asked what is the root cause of the neck shrinkage. So neck shrinkage happens because the neck, because there is an expansion. In ductile line, there is an expansion. So there is a reverse flow of from casting into riser during solidification, during expansion, during graphite precipitation. So that is the cause of, and if your neck is not correctly designed, then it remains open during the reverse flow. So if it remains open, then it allows flow of expanded metal into riser, which we don't want to happen. We want the expansion benefit to be inside the casting. So the root cause of the neck shrinkage is oversized neck. Okay? Understood? Okay. So I go to next question. How to avoid core zone shrinkage? I think this is a good question. Many times, like in impellers, we had no design scope to avoid core shrinkage because the core is uh, surrounded by metal from on all sides. So the best thing we can do is in some cases by allowing the core to collapse, so that when the core collapse, there's increased the cooling rate increases. But if the core is thin and the surrounding metal is thick, then there is really no way to avoid core shrinkage. So then in such cases, what I have done in particular in some cases, that we have uh, removed the core, removed the bore core, that is the core which goes into the drill. So we have made the drill solid, and then that avoided the shrinkage completely. So what I had to do was then I had to drill those bores and then supply the casting. So my operation in machine shop increased, but my shrinkage completely disappeared. So this is possible in certain cases. In some of the cases, we may have to think of some other possibilities, but avoiding core zone shrinkage in drills and bores, I think this is definitely possible. And I think whenever you have a problem, I think you should think about it. Okay, neck modulus is another question. I think I answered that above. What is the best way to remove liquid slag? So removing liquid slag is difficult. Avoiding liquid slag formation is possible. So I think what we can do is make our melting practice in such a way that we avoid liquid slag. So what is how we avoid liquid slag? So liquid slag is formed when there is a holding, when there is a metal which is exposed at high temperature to air, and then the liquid metal immediately reacts with the oxygen in liquid and in the air, and liquid slag formed. So when there is a holding, and if we have covered our liquid metal sufficiently, there is a furnace cover on top. Some of the foundries do that. So when there is a metal is getting poured and you are waiting for the ladle to come back, they will cover the furnace. So in that way, they uh, avoid interaction of the liquid surface with the air. So avoiding holding time, then covering your ladles during transport to pouring bay and during pouring. These are, and then cleaning your ladles regularly. Because if you don't clean your ladle, so next time when you tap liquid metal into the ladle, the earlier slag which is sticking to the ladle gets melted and then gets carried forward. So this is another thing which you must do to avoid liquid slag formation. Okay, then lastly, very informative. Okay, 1 minute. I think there are some more questions. One casting GM works. So I think one casting is round and similar to the one shown in PPT number 20. We have done circular gating and it has more amount of tar. Is it due to turbulence? So what I would do is some of the points I would like to give them more detailed answer. So you can share my WhatsApp number with the audience, and then they can share their, like for example, in this case, GM Works can share his drawing and his photos of the defect, and then I can give him a comment which is more relevant, more accurate to his case. So I think I will do that. Then how to avoid hotspot shrinkage. So hotspot shrinkage by uh, collect by giving feeder on the hotspot. So when you cover the solidification shrinkage which is happening in the hotspot, you are covering hotspot. But in many cases, your hotspot is not really reachable to riser feeding. So recently, I think in the IFX also, we had taken one booth. My German principals, Visio Meta, they have developed a software where you can identify a hotspot in the design stage itself. So when you start designing your pattern and then you want to see if you have a risk of your hotspot, then you run your upload your part drawing into the software. Then it shows you where are the hotspot. Then you add material, you reduce material, you make the drill, the bore solid, whatever we have discussed so far, and whatever you have been doing. Sometimes you increase the radii, sometimes you add material. So we increase taper, all those things. So you do all that and then see if your hotspot is getting reduced, getting eliminated. So that is possible in that software, Visiometa. So even before you design your pattern, you understand, you identify, and then you get in touch with your customer. You show him that these are the risks. Then he also sees it. Then he allows you to modify the casting design. And then you design your pattern with this modified casting design. And then you have avoided those hotspot risk. Okay. Okay. Then Mr. Swarnali, how to avoid reverse feeding, mean casting to riser. So again, that particular point, the neck design. So if you design your neck modulus in that particular range of 0.5 to 0.7 of casting modulus, then you are avoiding reverse feeding uh, risk. How to control below riser shrinkage. I think this is more possible when we are working in steel casting rather than uh, ductile iron. So many times ductile iron we use those sleeves with a breaker core, which breaker core is properly designed for that particular sleeve modulus. So I think when we are using products, using risers, using sleeves of correctly designed mathematical modulus, so these risks are low. But still, if you have a problem of shrinkage below riser, so please show me your problem case by some more information by showing your defect images, then your defect area where and how you have given the riser. So your gating, your methyling, your gating, and then your area where the shrinkage is occurring, and the photos of the shrinkage. So if you give me that information, I will offer my comments more accurately and more useful. I think those will be more useful to you. Then lastly, Mr. Shrirang has said too much graphitization. Yes, yes. So I think that also possible. More inoculation will cause, if you have done inoculation correctly, then it will cause more, more graphitization, more expansion. So yes, that is possible. So yes, I think that is the correct point, correct observation. So that is the observation which people have, those researchers have identified that more inoculation also increases your shrinkage risk. Correct? That is because there is more graphitization. Fast pouring, will it not affect directional solidification? No. Directional solidification depends on how you have, if you have progressive solidification, that means you provide your risers on the spots of maximum modulus, and then the next section has a lesser modulus. The next section has even lesser modulus. So in that way, there is a progressive solidification. And then when you provide a riser on the highest modulus section, then there will be progressive solidification, and whether then you pour faster, so that faster is dependent on your gating ratios again. So if you have gating which is pressurized gating, then I think you will be able to pour in that particular optimum time. So there will be no effect on your feeding behavior. But if you are pouring on a non-pressurized gating, and then if you are pouring faster in a pressurized gating, I don't see, again, if you have done it, the metering has been done in a way to promote progressive solidification. Again, in that case also, I don't foresee any impact on shrinkage behavior. Then Mr. Sayan Biswas, he says, we use sleeves in the pouring system and the casting is round shape cast iron, and it has machined at ingot area. We are facing hairline getting shrinkage. So again, I will request to share data with me and I will give you a solution in a detailed comment. Then Mr. Silambarasan, he says, using a chill to remove hotspot shrinkage, it works. But he sees a classic oversize effect, over hardening. How to rectify? Again, I will say the same thing. Please give me the data, show your case in more details, and I will surely respond in person-to-person communication. So I will try to understand why it is happening and offer you a solution.
Okay, sir. Thank you very much, sir. Actually, I think we'll share your information to the team, or you can put
Yes.
it in the chat box also, so
Okay.
that actually people can note it down.
I'll just share my contact here so that
Okay. Surely, sir.
my,
Yeah, with that, actually, we'll like to move forward actually with the vote of thanks. First and foremost, actually, I would like to express a sincere gratitude to our esteemed guest speaker, actually, Mr. Sharad Dhumane, for delivering such a knowledgeable and engaging session. Your deep expertise and practical insights actually into milk quality and its direct impact on shrinkage defects have been a truly valuable for us actually in the Foundry fraternity. I would also thank all the participants for joining us today and for the active engagement. Your interest and interaction made this session even more impactful. With this, actually, we conclude our today's session. We look forward actually for your continued support and participation in our upcoming technical initiatives. Thank you very much. Have a wonderful day. Thank you.
thank you. Thank you. Thank you very
Thank
much.
you. Thank you. Thank you very much. Thank you. Thank you. Thank you.
Thank you, team. Great, Sharadji. I think you have spoken, you're not spoken from the slides, you have spoken from your heart. That's what I could see for 2 hours,
That is a
tirelessly.
great compliment. Yes.
Yeah, tirelessly for 2 hours, 120 minutes, he spoke from his heart. That's what I could see. So
Thank
thank
you,
you
sir.
so much, Sharadji. I think it's a wonderful opportunity to meet you all again. I think we'll connect again soon.
Yes. Thank you, sir.
Thank you
I
very
think
much. Thank you. Thank
I think we had a good audience also. 35
Yes,
members. I think it is a good
Thank
audience,
you.
and I'm really happy to engage in
Right.
this way. Okay, sir.
Definitely.
Thank
Thank
you.
you, sir.
Thank you again.
Thank you.
Thank you. बढ़िया ट्रेनिंग चल रहा है, इतना सब खिच खिच के ट्रेनिंग बढ़िया से हो नहीं।
किस चीज का था?
ये बढ़िया